Okay, so let's get started with the first example then. So what we're going to be working on today is this idea of establishing relationships within our definitions, right? So what do we mean by those relationships? So usually when we talk about relationships, it's having one thing dependent on another, or one thing having influence on another, right? And typically the way that goes is that, well, anything in your definition, right, that can be parameterized, right? Whether it's a distance, whether it's a size, whether it's a length or a dimension or anything, right? Anything that you can convert into a numerical parameter, right, can be used then as an input into something else, right? And when you tie those things together, when you tie the relationship of one thing to another to its transformation, for instance, what you're doing is you're creating a relationship in which the expression of one object is tied to the characteristics of another, right? So, if we go back and look at the way that our components are laid out, right? We talked early on about the interface, right? And when we look at the interface, we can see very clearly, right? For instance, here under curve, you have something called analysis, right? Then you have a few tabs that are about creating geometry, right? And then you have a tab that's a utility, right? Which is basically modifying that geometry. You see that in the surface, right? Analysis, creation, utility, right? Meshes, analysis, creation, utility, right? And you even see it under the vector tab, right? If you look carefully, even though the vector tab looks a little bit different, you can see under plane, right? The top ones are about creating planes, right? And the middle ones are more analytical, right? And the bottom ones are more utility based, right? Creating points, analysis, and utility, right? So that's a common thing because analysis is important in order to extract data, right, from something that you have in front of you, right, to use. And then the data that you extract, you want to have some kind of effect on something else, on another piece of geometry, right? And so oftentimes what you'll see is that you'll have, a analysis component linked to a transformation component, right? Because, for instance, you can say, well, let's connect distance to scale, right? Or distance to motion, or distance to transform, right? All of those things, right? Rotation, right? So when we talk about creating relationships, that's basically what we're talking about. And that kind of creates this kind of iconic appearance for parametrically designed objects, right? It's because when we look at them, they're not regular, right? If anything, they're more irregular, right? They're not so much like uniform modules. They're actually more like huge databases of customized things, right? And we'll see that in the following example, is that what it is a matter of creating that relationship and then generating the variations based on a certain logic, right? So let's set up a very simple example for our first example, which is to say, well, let's look at pattern making, right? So typically when we're working with patterns, we'll start with something like a grid, right? So let's go to our vector tab under grid, and we'll start with a basic triangular pattern. So we worked with the triangle grid before, and if we remember, you can see that the X and the Y, they're all defaulted to 5, right? But, maybe we can allow ourselves a little bit of more range. And because of the order that they come in, right, and the orientation, we remember that the X and the Y, don't have a kind of one-to-one relationship. But that looks like about the right size grid to start with in order to get some idea of what we're working with. Now, the grid itself, we can give it a scale. And let's just use 10 as our scale for now. We can modify that later. And from that, we get these triangular cells, and we get the points, the center points of each of those cells, right? That's all there just as a framework in order to generate our pattern, right? So what can we use to generate a pattern? Well, we can use any kind of line really, but I think in this case, let's choose polygon, right? Because that will give us some flexibility. It offers the opportunity built in without having to go to our transform tab to modify the size, right? Using just the radius input, right? We also have the option to, can change the shape, right? So that, it can be maybe 5-sided or 4-sided or anything in that range. And then we're going to locate, let's say just one on each of our grid centers, right? And right now it has a default setting of radius 3. We can change that as well. Right? And you can see, that if just by playing with the scale, we're able to generate lots of different patterns, right? From, a very simple kind of relationship that we've set up, right? But this relationship is quite boring actually, and we wouldn't really call this parametric because the relationship is pretty linear, right? It's just like a one-to-one thing, right? And, when we talk about parametric relationships, usually we're talking about things that are differentiated, right? Or variable, right? And so instead of, manually inputting a single value like 6 for our radius, right? We can imagine a situation in which, these values kind of vary, right? On every occasion. So that not every single one of these are always the same value, right? And that would offer us the opportunity to create variation, but it can't be random, right? We can't just say, oh, let's create a list of random values to put in here, right? Because then, you don't have a kind of a logic behind the visualization, right? And if you go with something random, actually, you're not really creating a parametric relationship. You're just creating, variety without logic, right? So to do that, right, one thing you might consider is, well, how can I, what data do I want to use, right, to generate that logic from, right? And I think one of the most classic examples is using distance, right? The measurement of distance as a input value, right? For instance, for our radius here, right? So again, we could come to any of these analysis tools, right? And extract some piece of data to use as our input. But in this case, we're going to look specifically at using distance, right? And so you can find distance under vector, point, and in the kind of second category or second grouping, right? And the distance component just measures the actual distance that you have between one point and another point, right? So we already have a lot of points here, right? We have 1,500 points. So those will be, 1 point to measure to, but we also need a point to measure from, or more than 1 point to measure from, right? Let's start with something simple. We'll just create 1 point. And to create that 1 point, we have a couple options, right? So we have a container here for points, and we can either, put a point here and set that as our, input point. That makes it very easy to kind of drag it around our screen, right? Or if you wanted to keep, all your work kind of neatly inside your Grasshopper canvas, what you could do is that you could use, say, a input, right? And choose to use like an MD slider, right? So MD slider just means it's a multi-dimensional, right? So in this case, X and Y is probably makes sense for us. And I'm just going to increase it to a range of 50 to 50, right? We can see how that fits. And you can see right now, it's pretty small, right? Because it's inside. You look on the right-hand side, you can see the range that we have to work with when we're moving it around. So, there are a couple ways to make it fit better. One, we could modify, the values here, or we can scale our overall grid down so that it fits it, a little bit more nicely. In this case, that's what I'm going to do. And we can change the values here, to get it to fit a little bit better, right? So I think we'll also need to adjust this slightly. 50-50 is probably too small. Let's go for 100-100. And then increase the scale here. That would leave us with some flexibility in terms of the patterns that we can generate and this range of the scale that we're looking for, right? Okay, so now, so we've created this point in space right here that we can use the MD slider to move around, right? So you can see that that point is now, can be located pretty much anywhere along on that pattern, right? And I'm going to use that as my point A input, right? So once I've done that, you can see that the distance component is returning a number of values. And these values, right, are the distances between this point and these centers, right? So if we wanted to visualize that, just to see what it was actually measuring, we could do it like this, right? And you can see that each of these lines goes from the center, right, of our cell to that point in space. And when we move this point in space, that they follow, right? And the value that's generated using the distance component, right, is simply a measurement of the length of that line, right? So pretty straightforward. Now, what if, instead of inputting a single value right here in the radius and replicating that for every single point, the 1600 points, right, all having the same radius of 3, what if instead we gave those points values that were not uniform, right? You would see then that the pattern that gets generated is far more complicated, right? Because now you have a radius for this polygon. Some of them are 85, some of them are 60 something, some are 40 something, some are in their 20s, right? And every single one seems different, right, on that list. So we end up with something that's very complicated, right? And there are really, I think, two modes of thought in terms of the strength of working in parametric design tools. So one of them is that, it allows us to create variation and complexity, right? But in such a way that you maintain a certain logic, right? In which recognizable logic, right? So you're not generating something that seems random, basically. And then another way to think about it, though, is that, it allows us to expand our ability to conceptualize, right, what we're doing, right? So, for instance, if you saw, if I wanted to express this idea on the left-hand side here, right? how could you couldn't visualize that without the aid of computation, right? Basically, you can understand, if I did this measurement and then I created a polygon with that size, right? I can kind of understand, what it would give me, right? But there'd be no way for you to really visualize, because the computer is very good, right, at doing calculations, right? We as human beings are very poor at doing calculations. We're very good at understanding logic and concepts, right? So in this case, we're taking advantage of the fact that, well, we understand this, right, as an idea, right? But we can't calculate and visualize this, right, on our own, right? Because it's just far too complex, right? And so the other school of thinking in terms of parametric design is that, well, it offers us the opportunity to explore concepts that are beyond our human limitations, basically, right? So how you approach parametric design is up to you, right? But just know that those are kind of the predominant ideas in terms of using parametric tools in design workflow, right? So in this example, you can see that, well, by simply kind of playing with the extremes, right, and then modifying these parameters, right, I can generate, some interesting concepts, right, that are, beyond my imagination, right? But on the other hand, if I wanted to create clear logic, right, and have recognizable relationships, right, then, I would need to find a way to kind of modify some of this data, right? So in the past 2 weeks, the reason it's so important for us to be able to control data is that a lot of times the data that's coming out of one of these analysis components may not be so ideal for the application that you're working on, right? And so actually, I think a lot of people feel parametric design as a design philosophy means that you as a designer are kind of not able to cheat, right? It's not, you're not imposing your will on the design, right? And actually, all of it is data driven and it's, rational and whatnot, right? But of course, that's not true, right? Because as you know, you have experience, right, in Grasshopper, and you know that you can manipulate the data however you want, right? Once you have that skill, it also means that, well, you are driving the project again, right? It's not so straightforward as saying, well, that's what the data generated, and so that's the result that you're going to get, right? So our job in this case now is to modify the data set that we're given, right, to get a result that, may be more what we're looking for, right? So right off the bat, I think, if we wanted to have something where the logic was clear, the radius that we're looking for needs to be smaller, right? Because as you can see in this example, as we increase the size of the radius, right, the relationships become more blurry, right? And as those sizes get smaller, right, that relationship becomes much, much more clear, right? So right now, if we look at the data that we're getting out of, the distance measurement, you can see a lot of those, are in the 80s, right? And that range is really huge. It's like 80s down to single digits, right? So we need to find a way to reduce the size of, or the values, right? So that they're not so huge, right? So how do we do that? Well, of course, we could go to, for instance, our math tab, right? And we can say, well, I know how to reduce values, right? We can use division, right? And I can just take the values that are coming in and say, well, I'm going to divide, everything by, say, 25, right? And if I do that, right now, all of the values are now between, 1 and 4 or something like that, right? And then I can take those and I could use those as my radius, and I get, this kind of a result, right? And depending on the, the factor, right? Whether I'm dividing by 25 or 83 or, 10, right? It changes the speed at which the modification occurs, right? And so you can see here now there's a very clear logic in terms of what the relationship is, right? We can see that we have a point here in space, and the objects, as they're closer, the closer the object is to this point, the smaller it is, right? Up until a point out here where, maybe it's a little bit vague out here now because it's too big and there's so much overlapping and complexity, right? That you can't really see it anymore. But essentially, that's the kind of relationship that, was considered kind of parametric, right? Because it was generated out of a certain data, right? In this case, the distance data between those objects, right? So that's one way to do it, right? But there's actually a better way, right? And that's where we kind of get to our discussion about domains. So right now we're using a kind of single factor, right, to reduce everything. But you can see that the problem with the single factor is that some of them are already too small, right? And some of them are already too big, right? So while it's able to reduce everything, it doesn't offer us the ability to control kind of the minimum and the maximum, right? So to do that, we're going to use our domain tools, right? And specifically, we're going to use one called bounds, right? And we're going to use one called remap, right? So what this does is that we can input our distances, right, into the domain, right, min-max domain. And what that does is that returns, and I'm going to try to get a single value for all of them, that returns the range, right, in which those distances occur, right? So we can see here that the longest on any of those lists is 109.8 and the shortest is 0.6, right? So our biggest polygon would have been getting a radius of 109, and the smallest one would have gotten one that's 0.6. Now, we might say, well, back when we were looking at this originally, we had a 1 and a 2, right? And let's say we never wanted it to exceed the size of our triangle, right? That means basically, the largest radius we're interested in is like a 1, right? And then, everything smaller than that we can accept. So what we need to do is we need to tell Grasshopper the range that we're interested in, right? We know the range that exists now, right? And then the range we want, we need to define, right? So we're going to construct a domain, and that's going to be our target domain, right? Our source domain and our target domain. So our target domain, we said, was a value between basically 0 and 1. So if I just use a regular slider, let's say 0 as a start, 1 as an end. So the domain is 0 to 1, then existing, right? And then the values are the actual distances, right? And so what happens then is that the remap component will come and it will proportionally scale all the values that are on this list, right? So that they fit within our 0 to 1 range, right? And if we use these remapped values as our radius, you can see now that we still have our parametric relationship, right? In which the closer you are to this point in space, the smaller you get, right? But you never reach a situation, no matter how far you are, right, where you're exceeding, right, the size of your cell, right? So by understanding how to kind of work with numbers, whether you're using math operators or whether you're constraining using a domain, right, you have a lot more control, right, over the execution of your definition, right? And so that's, I think, enough for the first example. Let's play around a little bit to see, what happens since we took the time to kind of create a definition that's continuous and we didn't break it anywhere. If we, play around with some of these values, let's see what kind of changes we see, right? So now we can come here into our segments, right? We can change the type of shape. We can take our, let's say if we invert our range, right? So now when we inverted it, what we see is that, well, the closer we are to this point in space, right, the bigger, right, that geometry is, and the further you are away, the smaller it is, right? So we've created an inverse relationship, right, by flipping those around. Obviously, when we move our point in space, that changes the values, and therefore all the distances are changing. If we change our size, we expect that the overall grid will change, although the extent of where we can move our point is more limited. That's the top right that we can get to, right? And of course, the changing of the size and shapes, right? So that's our first example of working with influencers, and specifically looking at scale and distance, right? Okay, so why don't you try that on your own, see how that feels, and we will move on to our next example. Okay, so in the next example, we're going to look at a situation in which we have multiple points, basically. So we'll start off again with a fairly simple grid. Any of these? Let's just do a square one for simplicity. And again, some sliders to adjust the extent. And I'm just going to use one for both of them. Keep them more or less the same. Maybe another slider to control the size of each cell, right? So with that as a starting point, let's look at what the differences are, in this example compared to the last. So basically in the previous example, we saw that we could create a relationship between a point in space, right, and the scale of those objects, right? And, it's easy enough when you're only working with a one-to-one, right? Well, in that case, it was probably like more like 1 to 1,000 or something like that, depending on how big our grid is. But what happens when you have to evaluate for multiple objects, right? It becomes a little bit trickier. So let's look at an example using vectors, right? Fairly similar, I think, except for the fact that we will have multiple points to deal with. So here we're starting with a square grid, right? And from there, we're going to still use that distance evaluation, right? So we can go back to our vector and find the distance. And because we're working with 2 points instead of just a single point, we'll probably have 2 of these. Now, to set up our 2 points, we're going to use the MD slider like we did in the previous example, right? And I'm just going to adjust this range. It's going to be 300. Let's see. I want to visualize that, sorry. So you can see, yeah, almost. I just gotta get this there. So our slider now works within our full grid. And we're gonna do that twice. Right, because we're talking about what happens when we have multiple reference points. So you can see here, by default, we already have points from our grid, and they appear at each intersection, right? And so these points, well, first I'm going to flatten them. Actually, I'm going to use this flatten so that it's more clear for you guys. Okay, and so from there, we're going to do a distance evaluation, right? So we can know how far each point on this grid is away from the 2 points that we created, right? 1 point here, right? And another point here, right? So there are 2 points within that grid now. So if we have our, grid of points as point A, and then we split on point B, you can see that it returns to us 2 lists, right? And these lists are pretty similar. They should all have the same number of points, right? 960, 960, right? Because we generated 960, and there should be 1 comparison, right, for each point. And the range, right, you can see now is different, right? So the measurement from this point here to our first point on this list, right, which is probably in one of these corners. Let's just display that for you guys. So we can see change the size. Maybe that's big enough. So 0.1, right, or 0 rather, is down here, right? So it's comparing, or it's giving us the distance from this 0 to this point here, right? And it's telling us it's 303 units away. Whereas if we compare it to our second point down here, right, the 0 value is 120, right? So you can see now we have 2 full lists, right, where it's calculating for us the distance from each point. So before we start to work with the creating the kind of influence, right? The first thing we have to do is actually decide, right, which points on our grid, right, are affected by, which of the 2 points that we created, right? And to do that, we're basically going to use what's called a conditional statement, right? And so the conditional statement basically allows us to do comparisons, and you can find those in our math tab here. So under math and then operators, right, where we had our kind of math functions, you'll also find down at the bottom conditional statements, right? And those are those, like similar, equal, larger, greater than, smaller than, etc., right? So in this example, we'll just go ahead and use the smaller than, right? And then with the smaller than, what we're going to do is we're going to compare, right? We're going to compare the values in this list versus the values in that list, right? So actually, I should have left these out so you guys could see them. And be clear about what it is we're doing a comparison of. And so it will be one number, the first number, versus the second number here, right? Just like in a mathematical function, right? So all it's doing is comparing the numbers on this list and telling us one of two things. Is it or is it not smaller, this number smaller than this number, right? If this number is smaller than this number, right, it will return a new list, right? And on that new list, it will say true or false, basically, right? So you can see here that as it's doing this comparison, the first few values, right, are continuously false, right? Because all of these values up here are bigger than these values down here, right? But let's say we go down the list towards the other end, right? You can see that by the end of this list, right, the values down here are now bigger than the values up here, right? So if we go to our panel here and check again, you can see that the values are now all true down here, right? So at a certain point, there's a kind of flipping over, right, where they become kind of not so obvious, like which ones are true and which ones are false. So you can see occasionally here they will start to be more mixed. And if you go towards the middle, you can see that it's now, it's true and false is alternating, right? So, okay, so now that we've done that evaluation, what can we do with it? Uh-oh. What can we do with that evaluation, right? Well, if you remember, a lot of our list organization tools, right? For instance, these ones under sets and lists, as well as sets and sequences, like the culling stuff, right? They all use a certain pattern, right? So for instance, call pattern, right? We inputted true and false, right? In order to remove or add items to a list, right? And the same is true here, right? For some of these things like weave or pick and choose, right? In this case, what are we trying to do? We're trying to divide, right, all these points into two lists, right? One list of points that are closer to point A, right? And then one list of all the points that are closer to point B, right? So if we go into our sets and we look at our utilities or our tools, right? The one that will help us do that is this one called dispatch, right? And we looked at dispatch before when we were introducing list stuff. Now you can see here clearly there's something called dispatch pattern, right? So dispatch pattern accepts true and false, right? And by default, you can see that it already has a true false alternating pattern, right? We're going to replace that with the true false pattern that we got using our conditional statement, right? And then our list, right? What is our list? Our list is the overall points, right? So we're just going to take our points from here. I'm going to move that so we can see the connection clearly, right? And now I have two lists instead of just one, right? One list of all the points that are closer to point A, and another of all the points that are closer to point B, right? So from there, we can check quickly, because we don't know just by looking. I mean, maybe you could figure it out, right? Just by looking at the position to see if list A is associated with these or list B is associated with these, right? We don't know very clearly yet. So I'm going to use some curves, right, to make that very clear. So here is point A, and we're going to connect list A to point A. So that looks right, right? Because our point A is here, right? And clearly all of these, right, are the points that are closer to point A than to point B, right? So now that that's clear, we can get rid of this because we don't really need it. And what we're going to do instead is we're going to draw a vector, right, to create a kind of graphical representation of what's happening. So let's go to our vector tab, and we're going to say, let's do vector with 2 points, right? Because we have, a start point and an end point, right? So we have one for this one. I'm going to copy it again, this one, and then link those back to our original points of reference. And so you're not seeing anything yet, right? And it's not important. The reason is that all that this does is give you the actual value, right? It doesn't do anything graphically for you. So in order to get a graphical representation, right, actually what you would need to do is you have to go to your display, right? And you have to use, your vector tools, right? This is also where, we got our point list and stuff like that. But before we go there, we want to set up a certain relationship too, right? So all we've done so far is to decide which points are associated with which points, right? We haven't created our relationship yet, or that similar to the one that we had before, right? Before, in our previous example, we had a relationship that scaled the shape of a polygon, right? So that was bigger or smaller depending on the distance it was from the object, right? So in this example, we're going to use vectors instead, right? Although we're still going to be using our distance. So if we come back here, we can add a couple distance evaluations, right? And we're going to evaluate for the distance from our list, right? So we have a vector evaluation and a distance evaluation. So list A, this point, goes back to this point. And list B, this point, goes back to this point, right? And then from there, we're going to use a amplitude. And that's going to help us to determine the length, right, of the vector that we're working with, right? So I'll move this up a little bit to make some space. So if we associate the amplitude with our distance and the vector there, now we'll generate vectors that are, of a different length with a list of start points. And at the moment, it looks just like as if I had drawn those lines before, right? Because what have we done? We've made the distance, the amplitude, right? So the length, right? And so it's just gone and completely connected it, right? So in fact, what we need to do is we need to reduce, right, the value so that the length is less, right, than the actual distance, right? So what do we do to do that? We go ahead and we take our math tab, and you could do it a couple ways. You could do it using a domain, right? Similar to the way that we did in the last example. Or in this case, we can just use a division factor, right? Number slider. So by doing so, actually, this range is wrong, right? I need to divide by values greater than 1. So 1, and then let's say this is 10. So you can see as I do this, what's happening. Let me hide this grid now because I think it's blocking our view. Maybe we don't even need these points. There we go. So you can see that as I make that denominator larger, right, the ones furthest away still have the longest line, right, the longest vector. And as we get closer to the point, you know, that length gets really short, right? So we're able to create already this kind of look that we're after, right? And I'm going to change this down a little bit. 0.5. Maybe 5. Interesting. That didn't. There we go. Well, that's too small now. Sorry. Okay, so that's okay now. Right, so we can see that we've still maintained, you know, we can still have this kind of, the logic is still intact, right? And we can do that for both sets. I think I connected something wrong. This one still belongs to here now. There we go. Right, so we can clearly see now that here in this example, we have a situation where all of the points, right, that we saw are closer to our A point or a B point. They are only responding to those respective points, right? I'm not getting any interference between those two. And that's all because of the application of our conditional statement, which helped us to develop a pattern, right? To dispatch, right, our list into two separate lists, basically, right? So now if we come back into our original, the first part of our definition, where we have the empty sliders, as I move around, you can see that that evaluation is happening, you know, in real time, so long as, again, while you're writing your definition, there's no break in the logic, right? So we talked about that. Everything flows from the left to the right side, right? So as long as everything is connected correctly and you don't have any additional things that are being added separately or any things that would break the logic, then that means that anything that you change, right, from beginning to end, right, will still give you a valid solution, basically, right? Okay, so that's using a conditional statement to work with, creating relationships and using influence and attractor points and stuff like that. All right, so next, why don't you guys try that again on your own? And next we'll go on to something a little bit more just for fun towards the end of the lecture. All right. Okay, so in our prior examples, we looked at creating a relationship using a distance function, right? And relating up, points in space to scales of objects, right? We also looked at vector directions and stuff like that using multiple points of reference, right? So how you kind of organize your data in such a way that, the relationships are clear, even if there are multiple participants, right? And so in our final example for the day, we're going to be looking at a situation where you have, instead of, multiple points of reference, you're having multiple types of relationships that are being defined, right? So, you might have something that's scale related while simultaneously having something that's positionally related, right? So like I mentioned before, right, we're using distance a lot in this because it's very kind of straightforward and easy, but a lot of our analysis tools, right, are basically there to help us establish these relationships, because any piece of data that we can extract from our definition or our geometry can be used as a point of generation, basically. So in this example, we're going to look at an instance in which we're setting up multiple relationships simultaneously, right? So let's go ahead and start again. We'll use a grid just to generate our initial geometry. I'm going to pick here a triangular grid. And for the purposes of this example, I think I'll limit the size at first, and then we can, expand on that later on. But we'll start off small to keep things kind of clean and straightforward, right? So we're working basically with just, one grid, right? One triangle. I do want to be able to change the size, however. From there, we're going to think about this triangular geometry and what are the different ways that we can modify it, right? So if we were saying, okay, we're going to do more than just do kind of a scaling factor or something like that. In fact, in this example, what we wanted to do is, let's say, reference a point. So I'm going to go ahead and create a point here. And this time I'm just going to drop a point in and reference it using set one point, right, to bring it in. So you can see now, that point is reflected here. And what I want it to do is I want it to have this triangle, right, orient or transform in such a way that it responds to the position of this point, right? So as I move this point around in space, right, this triangle will respond to that, right? So how do we do that? Well, first, let's go ahead and generate a surface instead of just lines or just a cell, right? So to do that, we know that the points here in this triangular grid, right, that get generated are points that are in the center of each cell, right? Which is not very useful for what we're doing in this example, right? Because I'm not trying to, I'm trying to actually create a surface from the cell itself, right? So one thing you could do, of course, is you could come into your surface tab, right? And you might think, well, what if I could just draw a surface from that cell, right? But having this surface afterwards is actually less useful for us because we're not ready to really, have a locked in geometry, right? What we want is actually to be able to create a geometry that will be able to transform, right? And so instead of directly drawing a surface, I think what we need to do, in fact, is to extract some information from our grid, right? And to use that to redraw the surface itself, right? So in this case, we have already a triangle here. And if we look at the data that gets outputted from our cell, you can see that, well, it's giving us a polyline curve, right? So this is kind of one thing, which is, again, like that surface, not particularly useful because it's too fixed, right? So if we want more flexibility out of it, what can we do? Well, we can try to rebuild it. And we can do that using our analysis tools, right? To extract some of its basic geometrical data, right? So in this case, if I go under curve and analysis, I can, throw this polyline curve into any of these to get more information from it, right? And in this case, what I want is actually not under curve, but under surface, right? So it's this one called BREP edges. Now, the thing about the BREP edges is that actually, because it's not a surface, that's not going to work. So I'm going to actually go back to my curve tab first, and I'm going to use an analysis component called discontinuity, right? So right now, the default data type that gets output from this cell is a single polyline curve, right? So this object. So if I wanted to break that down into its components, what I could do is I could rebuild it, right? And so if I wanted to rebuild it, I could extract, for instance, those edges, right? The corners using the discontinuity, which will evaluate, right, where those lines meet up. And then from there, I could go about kind of redrawing that surface the way I wanted to, right? And in this case, I can go ahead and use my surface tool or surfacing component, 4-point surface, which will also work fine with 3 points, right? Now, from here to here, though, you can see that we have to negotiate the data type again, right? Because here it's expecting 3 points in space, right? Whereas in our discontinuity component, it's outputting, each of those points, but all on a single list, right? So what can we do, right? Again, we're trying to negotiate between one set of data and another expected data, right? So to do that, we'll go to our data management tools, right? And we'll look through what we have available to us. In this case, under list, we have a component like that we talked about before called list item, right? And with list item, if we input our list into it, it will allow us to extract specific values from our list, right? So in this case, you can see if I wanted value 0, right, I just changed my list input value to 0, right, which is the default. So you can see that the item here that's being output will be this first point, right? Now, of course, if I wanted to have all of these on the separate, to be separated out, right, and then be able to plug them into here, you could do this 3 times, right? And then say this is value 0, this is value 1, this is value 2, right? And so now I would have these 3 points and I could connect them up, right? And once I connected them up, you can see that I got my surface, right? Of course, a grasshopper knows that's stupid. So if you come in here, you can see there's a plus and minus. So what you can do is you can add parameters, right? And it will automatically assume that, okay, so you want them to be listed out like this into separate outputs, right? Which means I can just, make my connection like this, right? And get the same result, right? Okay, so now that we've done that though, I want to be clear about, which point is where, right? So we're going to go back to our list, then change this to a something, right? So we know our 0 point, right? Corner A is here, corner B is here, and corner C is here at 2, right? So that establishes the the main kind of structure for everything that we're going to do next, right? Now, what is it that we're trying to get? Well, so from here, we've managed to draw that surface and extract those corner points, right? Now, if we wanted to have a triangle shape, right, that had, orientation towards this point, right? What could we do? Well, we could say that, okay, we want to redraw, right, this triangle so that it points at this spot in space, right? How would we do that? Well, the way to do that is to omit one edge of our triangle, right, one corner of our triangle, right, and insert a third point, right, at that location. So, and substitute that when we do the redraw, right? So to do that, what might we do? Well, we can take this surface now, right? And we can evaluate the edges using our surface breadth component, right? To evaluate the edges of that geometry now that it's a surface. We don't need this one anymore. And you can see here that under naked boundaries, there's 3 lines, right? So I'm assuming this is, line 0, line 1, and line 2, right? The 3 sides. So if I wanted to say, okay, I'm going to omit number 2, and I'm going to create a third point midway between 0 and 1, and then pointing in this direction. The way I would go about that is to first, of course, find the midpoint, right, of between 0 and 1. How do you find the midpoint? Well, obviously, right, because we know that in order to extract information, right, we need to go to our analysis tools, right? So what are we analyzing? Well, we're trying to find the midpoint of a curve, basically, right? So we're going to go to curve tools, we're going to go analysis, and we're going to say, okay, which one here will let me find the midpoint? And this one called curve middle sounds promising, right? So when I connect here naked to curve midpoint, right, you can see that 3 points appear, right? 1, 2, 3, because it's evaluating for all 3, right, of those sides. And that's fine. We're not going to use all 3, but it's fine that they're there, right? And you can see here that it generated all 3 of them, right? Now, from that point, we need to draw a line, right? A line that indicates the direction that we want the third point to go, right? And that's basically towards this point that we created. And we want it to start, right, from this point here in the middle, right? So, of course, we know that there's a line tool, right? That's, from one point to another point. But what we're interested here is actually not that line. What we're interested in here is actually the direction, right? So we're going to use a vector instead. And we're going to use one. Actually, no, we want the line, but we want to use a line that's controlled by a vector, right? So this line, the SDL line under primitive, right, under curve primitive, will allow us to define a start, a direction, and a length, right? So in this case, our starting point is going to be one of these midpoints, right? We didn't say which one yet. And to do that, we're going to go back to our line, right? We're going to say, okay, that one. And let's see. So there we go, right? Because this is defaulted to 0, so it found the first value on that list and it ignored the second two, right? And so it's starting the SDL line, right, from that point between the midpoint of 0 and 1, right? Now we need to define a direction as well. So the direction we define using a vector, right? And so the vector, we can come to our vector tab and we can say, look at our vector components, right? We want to do a vector from 2 points, right? The first point is our midpoint here, right? And the second point is our point in space, right? The one that we wanted to have influence on, right? So that then provides a direction, right? The vector is the direction, right? So now you can see once we gave it a direction, right? This line is now pointing to that point in space. So if I move this, right, it responds immediately, right? Now you'll also see that this the vector has the length, right, which is the distance between here and here. And if you were to connect them directly, right, obviously because it's a one-to-one, the distance measured and the distance that you want the line to draw, it's just going to connect them, right? That's, I don't think, what we want in this example. So let's create a different relationship using our math function, right? So again, we could do it in a number of ways. We could use our domain to define a specific range, or we could do it using a divide function, right? In this example, let's go ahead and use the domain. We'll define a minimum and maximum, the domain that we want, and we'll do a remap, right? So the minimum and maximum will come from our length here, right? And that will go to our source. The value is going to be this will be our target. The value will be our vector. And then our range we can define manually. Again, let's just use a slider for now. So we define a range between 0, say 1 and 10. And we use that as our length, right? And in this example, you can see that even 1 is too big because of the scale that we're working with. So what if I move this? Yeah, there we go. There. Okay, so now basically this line is responding the way that we expect, right? Now the easy part then is to now draw this triangle, right? That reflects the actual component that we're interested in working with. So to do that, again, we can use any of these surfacing tools, but this one makes sense. So we're going to use well, here, first of all, we have a line as an output. So we need, again, to use the analysis tool. We want to find under curve the endpoint of our curve here, right? Because it has 2 ends on that line, and we want the end to be corner, let's say corner C. And A and B, right, are going to come from here, from our original. So that's our new triangle, right? That points at this spot in space, right? And you can see that the size, right, of that triangle will also change depending on its proximity, right, to the point. And that's controlled using the length here. So we have some control over the length, right, as well as the directionality, right, of that surface. So that's all there is to it, right? But that's the kind of easy part. I mean, that's the kind of difficult part. There's a right, but you know, let's say what's fun though is that now that we've done that, we can come in and say create a whole field. And every time I move this point in space, the whole field is responding and everything in that field is pointing. This is probably too big to see, so I'm going to make this smaller a little bit. Everything in the field is now responding to the position of that point. And let's scale that up a little bit so it's more clear. So you can see now here that, you know, all the triangles that are generated in this side are pointing that direction, whereas all the triangles that are generating this side are pointing in this direction, right? Because they're all aiming for this point here in space, right? If I move it around, you can see that, you know, it's responding in kind, right? So essentially, this will conclude our discussion about, you know, using influence and establishing relationships between different geometries. You can see now how, you know, you can do it really with any piece of data that you can extract, right? So whether it's distance related, like this line, right? Or whether it's directional, right? Like we took the direction, use of, you know, the vector analysis tool to find the direction of a certain point in space to another point in space, and we used that as the input data, right? It's, you know, there's a lot of flexibility in terms of how you want to use the tool, right? And what things you know, what kind of relationships you want to create, right? And I think that's really the key of working in, you know, in a parametric tool is, you know, seeing the results of those relationships visualized, basically, right? So, you know, up until, you know, at the very beginning, we were working with only just one cell, right? And up until then, it was all very clear in our mind what was going to happen, right? But again, it's something that, you know, as you increase the value in the numbers, right, it becomes much less, you know, much more difficult for us as humans to be able to understand large numbers, whereas, you know, in the machine, all of these things come very easily, right? And because of that power that it gives us, it allows us to, you know, play with design in a different way, right? Because now, you know, we can actually visualize it, we can see what's happening, and we can make adjustments, right? While at the same time maintaining that same logic, right? So hopefully that you find that useful in your design practice.